In this video, we're going to do some derivatives that include practice of the quotient and product rule. So the product rule says that if we're talking about the derivative of f of x times g of x, where they are each differentiable functions, then the derivative is the first times the derivative of the second plus the second function times the derivative of the first. The quotient rule says that if f of x and g of x are differentiable, then as long as g of x is non-zero, the derivative of the quotient is the low d high minus high d low all over the bottom squared. So here are the functions that we'll take the derivatives of. So f of x equals e to the x cosine x over x to the fourth plus 5. F of theta equals tangent of theta over 3e to the theta. G of t equals t to the third minus 5 to the e over pi squared. G of x equals x squared plus 3x to the sixth over x to the fourth. F of theta equals the seventh root of theta cubed times cotangent of theta. H of x equals x squared plus 4x divided by 7 natural log of x. And g of x equals 3x to the sixth times cosecant of x plus natural log of x. So pause and try those out on some paper, and I will go through them one by one. All right, for our first derivative, f prime of x is equal to, so this is a quotient rule, and when we do the quotient rule, there's going to be basically a product rule inside of that. So we're going to start by doing quotient rule. So that's low x to the fourth plus 5, d high, derivative of the top. Now we're using the product rule. So the first times the derivative of the second plus the second times the derivative of the first. Derivative of e to the x is just itself. So that was low d high. Now minus high e to the x cosine x d low. Derivative of x to the fourth is 4x cubed, plus derivative of 5 is just 0. All divided by the bottom squared, x to the fourth plus 5 squared. So that's basically our answer. There's not a lot we can do to simplify it. I'm just going to write that as having an e to the x out front of the whole, of the whole thing. X to the fourth plus 5 times cosine x minus sine x, just reversing those two to have the negative inside, just a way to make it look slightly prettier, minus 4x to the third cosine x, all divided by x to the fourth plus 5 squared. Okay, so our next function is f of theta is tangent theta over 3e to the theta. So f prime of theta is low 3e to the theta, d high. Derivative of tangent x is secant squared x, minus high tangent theta, d low. Derivative of 3e to the theta is 3 constant multiple rule times the derivative of e to the theta is just e to the theta, divided by 3e to the theta squared. So we could rewrite that as we've got a 3e to the theta and a 3e to the theta that can cancel with one of those 3e to the thetas. So we've just got secant squared x minus tangent theta, all divided by 3e to the theta. Okay, next we've got t to the third minus 5 to the e over pi squared. So we could use the quotient rule on this one, but I'd recommend simplifying it instead or rewriting it. So we're just rewriting g of t. This is the same thing as t to the third over pi squared minus 5 to the e over pi squared. And so we could also see this, if we want to, as 1 over pi squared times t cubed minus 5 to the e over pi squared. So e, pi, 5, those are all just constants. So this whole thing is a constant. And this is just 1 over pi squared, also a constant. And so we can just use the power rule and the constant multiple rule to take its derivative. G prime of t is equal to 1 over pi squared, constant multiple rule, times the derivative of t to the third, that's 3t squared, minus derivative of a constant is just 0, and so g prime of t is just 3 over pi squared times t squared. So that is our derivative. So we do not need the quotient rule. If you did use the quotient rule and you employed it correctly, then you would still get the same answer once you reduced. Problem 4. We can also use simplification or rewriting to avoid the quotient rule here as well. So we could rewrite that as x squared over x to the fourth plus 3x to the sixth over x to the fourth. And then we could continue to rewrite that. We haven't taken a derivative, just rewriting. X squared over x to the fourth is x to the negative 2 plus 3x to the 2. When we divide, we know that x to the a over x to the b is equal to x to the a minus b. So we're just using that rule of exponents to simplify each of those. So g prime of x is then equal to, using the power rule, negative 2x to the negative 3 plus 3 times 2x to the 2 minus 1 is 1. And so g prime of x is equal to negative 2 over x cubed plus 6x. So that is our derivative. Again, if you did take the derivative using the quotient rule and employed it correctly and then simplified, you should get the same answer. All right, f of theta equals the 7th root of theta cubed times cotangent of theta. And there's a little product there. In general, if you see two functions written right next to each other, you assume that they are multiplied together. So we're going to do a quick rewriting of that. That's equal to theta to the 3/7. Remember, the root goes in the denominator of the exponent times cotangent of theta. And now I'm going to use the product rule to find that derivative. F prime of theta is the first times the derivative of the second. The derivative of cotangent is negative cosecant squared x, negative cosecant squared. So first times the derivative of the second plus the second cotangent theta, and that was a theta, not an x, sorry, plus the second times the derivative of the first, using the power rule, 3/7 to the theta, 3/7 theta to the 3/7 minus 1, that's negative 4/7. And so we could rewrite that. F prime of theta is equal to negative the 7th root of theta cubed times cosecant squared theta plus 3/7 times cotangent of theta divided by the 7th root of theta to the 4th. So that is our f prime of theta. All right, h of x is x squared plus 4x over 7 natural log of x. We do need the quotient rule for this. So h prime of x is equal to low 7 natural log of x d high 2x plus 4 is the derivative of the top minus high x squared plus 4x d low. Derivative of 7 natural log of x is 7 times 1 over x, all over the bottom squared, 7 natural log of x squared. And so we could do some rewriting if we wish. This is 7 natural log of x, I'm just going to leave this 2x plus 4, minus, and let's distribute this 1 over x. So minus 7, 1 over x times x squared is just x. Minus is still out front. 7 times 4, 28. And then x times 1 over x is just 1. So just leaving it like that. All divided by 7 natural log of x squared. We could also write that as 49 times the natural log of x squared if we wish, or we could leave it like that. So that is our derivative. And then last one, so here is a product rule, and we could distribute and then we do the product rule twice, or we could leave it as this, and then this is just our first function and our second function. So g prime of x is equal to the first, 3x to the 6th, times the derivative of the second. Derivative of cosecant is negative cosecant x cotangent x, plus derivative of natural log of x is 1 over x. So first times the derivative of the second plus the second, cosecant x plus ln x, times the derivative of the first, 18x to the 5th. And so that is our derivative. We could do some rewriting here if we wish. G prime of x is equal to negative 3x to the 6th, cosecant x cotangent x, plus 3x to the 6th times 1 over x, that's 3x to the 5th, plus 18x to the 5th cosecant x plus a natural log of x. We can't believe that like that. And that is our derivative. Just as a side note, when something like, if you have something like cotangent of x times 1 over x, something like that, these things do not cancel, you cannot combine, so can't combine or do anything like that. This is not equal to like cotangent of 1 or something like that. No. So that's just a side note. If something is inside of a trig function, sine of x times x, like this is not equal to sine of x squared, etc. If it's inside the trig function, it's inside there, unless you're using some special trig identity. You can't get inside of that and multiply it, do anything with non-like terms.